thanks for allowing us to present our work. Actually, I'm going to present mostly the work done by Diego Garay, who was a PhD student in my group and also postdoc, and is also in the room connected. So if there are complex questions, Diego is the person with authority who answer them all. So we are the group that developed IoChem BD. IoChem BD wanted to solve our problem. We are computational chemists. And since many time ago, we realized that we are managing too much data. We have problems in organizing our data and storing the main results. Also in publishing, we had data unconnected. So we had a mess with the data. And we decided to develop IoChem BD. IoChem BD is a web platform that covers, say, all the pipeline from the data we produce in the supercomputers, say, till we include that data in a paper that is published. Our platform is built from several modules which are connected and that allow to deal with the data when it's in private mode and then publish the data following the standard pipeline of a manuscript publishing process. We can embargo the data while the paper is under reviewing, and finally we release a DOI with all the data set, which is perfectly fair. So we wanted to transform our results into fair data, and IoChem BD allows to do this very easily. We have unified several computational chemistry formats into what we say the CML language. And while IoChem is a web interface, as I said, but it also can be, you can interact with the platform via Linux shell or even with our new REST API interface. So the goal of IoChem was to generate DOIs for manuscripts and for, say, data sets generated by computational chemistry methods. But so it covers perfectly this pipeline from the data production to the papers accepted. But in many of our projects, we deal with reaction mechanisms. And we realize that while we were able to publish the individual calculations through our website and generate fair data from that, we have any way to publish and to make the reaction mechanism available. So actually the reaction mechanism is additional information, additional knowledge that we generate on top of the individual computational calculations. So the missing link in our solution was actually to add the chemistry, which is on top of our numerical studies. So we decided to start introducing reaction networks into IoChem. And while reaction networks, you all know, we treat them as graphs, as intermediates being the nodes, and the chemical reactions, actually we know it as edges. And in our world of computational chemistry, the edges contain a transition state, and you have reaction energy barriers, etc. So now IoChem can handle reaction networks. And I'm just showing you here a couple of screenshots of our module that allows to visualize complex reaction networks, but also to edit the network. So we can discover the network automatically, as some codes allow, but we can also build the network by hand, if it is not that complex, and edit and construct the network as we need. And then we realize that to put all this together, we needed an ontology. So an ontology is the way we found to connect the computational chemistry results with the chemical information and the chemical knowledge that is contained in a reaction mechanism, and with that to build what is known as knowledge graphs. So we define what is called OntoRXN, which is a very simple ontology, and it it's not intended to answer very complex semantic questions, but we find it's the way to connect the individual computational calculations with a reaction mechanism. And for that, we define 4 classes, the individual calculations that we assign to a given chemical species, then chemical species in a reaction network combine in network stages that they form part of the reaction steps. So a reaction step actually connects 2 network stages, and each network stage can contain several chemical species, and for each species we can have different computational chemistry calculations. In that way, we find that was an easy way to organize the information and to add the knowledge about the mechanism on top of the single, say, DFT or computational chemistry calculations that we usually run. I have to say that there is an ontology related to computational chemistry, and we partly use also that initiative. And the rest, I think you more or less know about that. Yeah? So we transform a simple reaction mechanism into a knowledge graph, where all the nodes and all the stages and all the edges of the network are highly interconnected according to our classes, and this builds the knowledge graph. The knowledge graph can then be queried using high-level languages. These queries quite close to natural language if the semantics allow that. And building these queries in SparkQL, we can extract the information we want from the knowledge graph that actually contains all the information about the system. And I'm finishing with a couple of examples. For instance, we had in one study that we characterized a reaction mechanism, a very simple reaction, one-step reaction, organic reaction, it's a decarboxylation, with a side product. And we did that study with 29 different solvents. So we had all that information in the knowledge graph. And then by just selecting the single calculations and the different stages of the mechanism, we can recompute from the single energies, we recompute the relative energies and the transition state energies and rebuild a reaction energy profile automatically. For instance, in this case, this is built automatically with a simple script that queries the knowledge graph. The advantage of this kind of queries is that those queries are general and can be applied to any kind of reaction, any kind of mechanism that is written in the form of a knowledge graph. In another example, much more complex, if you want to say that, we in part could answer some of the questions that Mark previously raised. For instance, how we can predict or how we can assess the distribution of chemical products on a given mechanism. We have, this is not the query that a knowledge graph has to answer, but with the information we have in the knowledge graph, we can easily automatize answering those kind of questions. For instance, we can select all the reaction stages and species, and from there, with the energies we have, we reconstruct all the reactions, and we can perform automatically, generate automatically microkinetic simulations from all the data that is already stored in the knowledge graph. So automatically, with a simple query plus some post-processing, okay, because a knowledge graph does not know how to run microkinetic simulations, and it's not the goal. But we extract all the data from the knowledge graph and plug automatically the data in a simulator, and we can get the distribution of products along time, or know exactly which time we have maximum conversion of a given reaction. So it's as simple examples of what we can do with the data once is in the form of a knowledge graph. What we are today. So the present status is that Diego Garay developed a lot of very nice tools to do these all processes almost automatically. So this OntoRXN is the ontology definition and is available in GitLab. Diego wrote several tools that allow us to manage and to gather the information in IoChem together with the chemical reaction network and generate the knowledge graph. We set up a test server with a database instance with our knowledge graph that can be found in this URL. And recently we are having discussions with a community of chemical modelers. So this is a community of groups working in combustion reactions, where the chemical reaction networks are quite complex, and they have their own databases, several databases around the world. And the goal of this community is to find a way to transform all this information in a fair fashion. And we think that they understood that our ontology can be a good tool for that. And let me just finish letting you know that we got an Oscars project. This is a project from the European Open Science Cloud that will support IoChem development for the next 2 years. We are planning some new software improvements in the platform, specifically include semantic models in a more wide way. And well, in these next 2 years, we hope that new academic institutions will set up nodes of our distributed database and use our platform. We expect to set up a cluster on computational chemistry under the platform of this European Open Science Cloud. And we plan to organize workshops, webinars, etc. So I think that we will have opportunities to meet again in the near future. And basically, this is a summary of our aims. So we think to standardize our data interoperability and use the knowledge graph to collect the data and to enable smart questions, not very complex and too high-level questions, but simple questions that allow us to manage and automatize data treatments. And we think that our ontology together with IoChem BD can be used a good tool for many chemists. At the end, in these very two simple examples, we may automatically rebuild reaction energy profiles or automatize microkinetic simulation or any other treatment that you may have in your mind. And that's all. Thanks